So we're going to do some review here today of some Chem 50 stuff. And again, hopefully this is review for you, I hope. Then next time we will get into official Chem 51 lecturing, which is kinetics is where we're going to start. All right, so as I mentioned before, these will be recorded. Hence, again, the microphone I'm wearing, and again, I'm going to be writing on the tablet, so everything will be up on there. So let's. It's been summer. I haven't written in a long time. Let's try this again. All right, so Chem 50 review here. And there really is no notes for this lecture. I just kind of wing it off the top of my head, try to remember what happened in first semester chemistry. I was there once, I think. All right. So we'll start way back at the very beginning, obviously, with Chem 50 and things like that, and also important in our class, which is measurements, right? So measurements are really important. Measurements are what are sometimes referred to as being quantitative, right? They involve values and numbers. And when we take measurements, there's really two very important things, right? There's the number and obviously the units associated with it. And your measurement should always have both of those things, the number and the unit. Remember that if you just have a number like 100, it really doesn't tell you very much. You know, if I had $100, that's very different than 100 pennies, and that's very different than it's 100 degrees outside, right? So, which just seems to be every day these days. Every day seems to be 100 degrees. So you should always have a number. You should always have the units that go with it. A number by itself is pretty much worthless. It's really important when we do take measurements that you look at the equipment for which you are using and decide how far that you can take those particular readings. Remember, something that is qualitative is more like observations, like it's yellow, a precipitate form. Quantitative, again, is pretty much measurements. So if we had something, for example, like this, we'll call this centimeters here. And if we just say we were measuring my arrow, something like that. Every piece of equipment that you look at, you should always figure out what does the scale mean in terms of taking an actual measurement. So in this case, our big numbers here are basically 1 and 2. So our big sort of numbers, our lines are basically represents 1 centimeter of a difference. If we count up the lines from the first one to the second one, and when we do that, we typically always start on this one. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So there are 10 markings between 1 centimeter. Each of the small markings represent how much? Yeah, 0.1 centimeters, right? So this guy here would be 1.1, 1.2, 1.3, 1.4, 1.5, and so forth along the way. So when we do take a reading, we should always record, and there always should be numbers that pretty much no matter who takes a look at it, everybody agrees would be the same. So no matter who takes a look at this, everybody would agree it is at least 1.4, and we definitely should record that. That is what is sometimes referred to as the certain numbers in the measurement. And all measurements have some degree of uncertainty sort of associated with it. And in this particular case, if we look at the arrow, it is clearly not exactly 1.4. It's not exactly 1.5. It is somewhere in that ballpark. And that's really where the estimate would come into play in this case. And in this case, I might think it's like perfectly halfway between the two. And I would record something like 5 here, and obviously our units here. This is what is sometimes referred to as the first uncertain number. And in this particular case, we would want to record 1.45. Now, that first uncertain number is really where the uncertainty lies in this measurement, because again, somebody else may look at it and go, I think it's a little closer to the 1.4, so maybe it's like 4, or maybe it's closer to 1.5, you know, maybe it's 6. When we take a measurement like this really is what we mean, and what everybody's favorite thing is, these two things here. When we record all the certain numbers plus that uncertain number, that first uncertain number, that is basically what significant figures are. Yeah. Which would mean that this number here has 3 significant figures, right? They're all significant in this particular case. Where the uncertainty really lies in that last digit, that last significant digit, which would be the 5 in this particular case. Any questions on that there? Now, sometimes, you know, you do have to look at the scale. So if we had something like, so we'll go with 10 here and 20 up here. We'll call this some milliliters. We'll draw my wonderfully crafted graduated cylinder. That's why I failed art. It's okay. All right, so that is 10 milliliters. That is 20 milliliters, and perhaps we throw a liquid in there that's green. Everybody loves green liquid. There we go. By the way, when we put liquid into a glass container, what happens to the liquid in most cases? It makes a meniscus, right? The curvature of the liquid. And that is because the attractive forces between the liquid and the walls of the container are stronger, yes, than the attractive forces between the liquid and itself, the intermolecular forces, right? Which is why the actual volume goes up. That's also why we also read the volume in this case from the bottom of the meniscus, because the artificial carrying up of the sides doesn't really give us where the volume actually is. It's actually on the bottom, right? So the bottom of this is where we would want to read. So if we look at this, we have 10, and obviously we have 20 up on top. And if we count, we got 10 dashes between the two. Our big dashes here obviously represents 10 milliliters. That means that our smaller dashes in this case represents how much? 1 milliliter, right? So this would be 11, that would be 12, 13, 14, 15, 16, 17, 18, not really drawn to scale. Bad quality control at the factory here. So if we were to take a reading here and we read from the bottom of the meniscus here, everybody would agree that it is at least 13, and we would record that. Once again, here we don't see it's exactly at 13, so you know, maybe you feel it is like around there, and you record 13.4 milliliters in this case. These would be our certain numbers, right? And this would be our uncertain number. That would mean that this guy also would have 3 significant figures in this case, right? All 3 of them would be correct. You should always look at the scale, because for different pieces of equipment, it does change. If you have something that is digital and it displays it, you should always record all the numbers because they're important. Otherwise, they wouldn't display it on the digital display. Now, if we look at another sort of flask, for example, and in most cases, what we do when we take a reading is we're able to go to one more place to the right of the smallest digit is typically what you could do, but not necessarily always the case. So for example, if we had our same sort of 20, call that 30 milliliters here, really bad quality control on the lettering here and numbering. So if we do something like this here, now in this case, 20 should be over here. There we go. All right, so we got 20. Actually, it was right here, huh? That was 20. All right, so let me fix the quality control here at the factory. There we go. All right, so 20 actually was there, so perfect. So in this case, our big markings is 10 milliliters. In this case, we have 1 line, 2 lines, 3 lines, 4 lines, and 5 lines. So we have 5 of the smaller lines. That means each of the smaller markings in this case is how much? 2 milliliters, right? So this would be 22, 24, 26, and 28. Now, when we take our reading right from the bottom of the meniscus, between 26 and 28 is 27. Yes. There's not enough space in there to know where 26 ends, 27 begins, and all that good stuff. So the best you could actually do in this case is to record something like 27. That would have how many significant figures? Would have 2 Sig Figs. The uncertainty would lie right there at the 7, right? Is where the uncertainty basically would lie in this particular case. Any questions on that there? In addition, if we maybe go back to our drawing here, and let's say we were measuring something like dead on there on the 1.5. Do I record 1.5 centimeters? Do I record 1.50 centimeters? 1.500? I'm not sure. I'm just going to put extra zeros because it looks more scientific-y, right? That clearly is just a lot of zeros that you just wrote there. That's not the right answer. Which one should I go, or is there an actual difference between the two? Second one. Okay. So let's talk about, is there really a difference between doing both of those? And the answer is it probably is a difference, I'm assuming. So erase some of this here. So let's take a look at really like the first answer there, right? And that first answer in this particular case is 1.5. And in this particular case, 1.5 centimeters would have how many significant figures? 2 significant figures, which means in this particular case, the uncertain number is the 5, which basically you're saying this thing could be 1.5, but maybe it's like 1.4, maybe it's 1.6. And clearly 1.6 is like way over here. It is like nowhere near 1.6 or anything like that. And not even really near 1.4 either, right? So when we look at 1.50 centimeters, this one has how many significant figures? It does have 3 significant figures. The uncertain number is, it is the 0 in this case, right? And that uncertain number right there. And this is saying it could be like 1.51, maybe it's 1.49, which if we look at our scaling here, that is probably correct, yes? And because we do have the ability to go to the second decimal place here, you should record that. There is a big difference, and pretty much when you lop off a significant figure, you're pretty much making your calculation crappy. Yes, a lot crappier than it should be. So if you have the ability to do so on that particular scale, whatever you're using, and it hits something dead on a number, you should still record to the proper number of digits and carry the zeros with it. Otherwise, you're really making your measurement a lot worse than it actually should be in this particular case. Any questions on measurements or anything like that? So when we talk about significant figures, which is an important thing in chemistry, they say, there are rules for significant figures, right? So pretty much all non-zero numbers, right, are significant. When we talk about zeros, there are really 3 types of zeros. There are the leading zeros, which are not significant. So if you had a number like this, it would have 3 significant figures. We usually start left to right, and we don't start counting until we hit the very first significant figure, right? In this case, that would be the 1. So all those zeros would not be significant. There are trapped zeros or captive zeros, and those guys are significant. So those are numbers, zeros between numbers like 404. That's a trapped zero. This guy would have 3 significant figures. And there are the trailing zeros, which give people the hardest time. Trailing zeros are zeros that come after or at the end of the number, and they may or may not be significant. And what determines whether or not they are significant or not is there a decimal place, right? Or decimal point. And if there is a decimal point, then they will become significant. If there's not a decimal point, then they will not be significant. So if we had 600 written like that as a measurement, how many significant figures would it have? It would have 1 significant figure. It would just be this guy right here, no decimal point written. If we had 600.0, this would be how many? 4 significant figures. This would be significant. All these zeros here would be significant. They all come at the end. And because there is a decimal point in the number, it would be significant. The decimal point does not need to be near the zeros at the end. It just needs to be in the number somewhere. So if you had 0.000104003003000 centimeters, not sure how you made that measurement. How many significant figures would this have? I have no idea. I was just writing numbers. So let's see. So we're starting left to right here. So we're not going to start counting until we hit here, right? So that is significant. 0 there is significant because it's trapped. That 4 is significant. Those 2 are trapped. They're significant. Those 3 are trapped. They're significant. So that's 1, 2, 3, 4, 5, 6. Now we have all 3 of these zeros at the end. Are they significant? The answer is they actually are significant, and they would be significant because way over here there's a decimal point in the number. So this would be 1, 2, 3, 4, 5, 6, 7, 8, and 9 significant figures would be how many there are. So you want to always give your answers, obviously, in chemistry and in life into the right number of significant figures, right? Now, the uncertainty in a measurement does lie in the last significant figure, right? So where would the uncertainty, if this was a measurement, be? What number would be the uncertain number? The uncertain number or the estimated number? Is it the 2? Anybody else? Everybody feels good about the 2? Anybody feel it's a 0? Anybody feel it's this empty spot right about here? No? Oh, okay. So let's take a look at, so 12,000 written like that. If we were start counting, we would start counting here at the 1. That would be significant. That would be significant. Then our zeros here at the end, are they significant in this case? They are not. There's no decimal. So you would be correct. That would be the 2 here, would be where the uncertainty lies. So you would be saying, I think maybe it's 12,000, but maybe it's 13,000, maybe it's 11,000. In the world of measurements, maybe not. So it's a great measurement. There's a lot of variation between those 2. Any questions on Sig Figs or anything like that there? Obviously, a majority of the time we deal with Sig Figs when we are doing calculations. So a reminder that when you are using Sig Figs and calculations, we basically do a couple of processes here. We multiply or divide. And when we multiply or divide the number of significant figures, and the answer is equal to the number with the least number of Sig Figs. So multiplying or dividing, if you took 4.5 times 123, this would have 2 significant figures. This would have 3 significant figures. That means our answer should end up with 2 significant figures. Same thing, if you're dividing numbers, you go by the smallest number of significant figures as to what your answer should be. If you're adding or subtracting, we actually don't look at significant figures, but we look at decimal places. And it is the smallest number of decimal places. Is how many decimal places your answer should have. So if I was taking 4.111 and added it at 2.5, I'm going to try this without a calculator. That's a 116.6. In this case, my answer should end up being, this has 3 decimal places. This has 1 decimal place. My answer should end up here at 1 decimal place, which would be 6.6. Although 6.6 has 1 decimal place, how many significant figures does it have? It has 2 significant figures, right? So multiplying and dividing, we look at sig figs, it's the smallest. Adding, subtracting, we look at decimal places, and it is also the smallest. The reason for that is pretty much the smallest one is your worst measurement. Yeah, so your measurements are only as good as your worst measurement, like the weakest link, right? So you're only as good as the weakest link. So the measurements and stuff that you do is only as good as the kind of weakest measurement that you have going on there. If we do multiple steps along the way, we do need to sort of keep track of significant figures in all those cases. So, you know, if we had something like, come here, 3.20 times 14567, and then we divide it by 1.2. In this particular case, we would most likely do the top part first, right? It's in parentheses, and there we are multiplying basically 3 significant figures by 5. I wrote there, it looks like 5 significant figures. That means when we're done with the top, we should end up, technically speaking, with 3 significant figures up on top. The next thing we would do is divide those 3 significant figures by 1.2, which is 2 significant figures. 2 significant figures. And that means that our answer should actually end up with 2 significant figures, right? Do you really want to round a lot along the way if you get an answer and continue on? The answer is you don't really want to do a lot of rounding, right? Because the more you round, the further away you are going to move yourself from the correct answer. So usually you want to keep a few digits past where you should and really kind of clean it up at the end is really the proper proper way of doing that. Some people call it keep some guard digits or whatever, but you want to keep some extra digits. Speaking of which, in terms of rounding, we do our normal rounding procedures, right? If it's like less than 5, we drop the numbers. If we're kind of 5 or above, we round up. We never want to do any kind of weird or crazy rounding, right? So for example, you know, if I had 13,333 and I wanted to round to 2 significant figures, what should it be? $13,000, any 13 people. So this written like this has 2 significant figures, right? This written like this has 2 significant figures as well. So they both have 2 significant figures. So they are correct in terms of significant figures, but there is a very big difference in the meaning of those 2 numbers, right? So if I owed you $13,333 and said, I'm just going to pay you 2 sig figs, here's $13. I'm probably not going to make it out of the room, probably, right? So, you know, if I gave you 13,000, maybe you throw me the $333 teacher discount and I'm okay. You know, they're around the same number. So in the interest of getting significant figures, you should never do crazy rounding where you actually change the meaning of the number. You always want to maintain that. And any questions on rounding, Sig Figs calculations? Other really important thing that people lack the ability to do is scientific notation. Yeah. So scientific notation, I'll spell it, is when we write really large numbers or really small numbers using this sort of format here, where the first n is actually a number between 1 and 10. That means not 10, not 100, not 20, or point something. It needs to be a number between 1 and 10 to the power of some number here, which is either positive or negative, depending on which way you go. So if you had 4, 2, 4, 5, and you want to write in scientific notation, we would go 1, 2, 3 places there. 4.245 times 10 to the 3. If you had 0.00325, you would go 1, 2, 3 places, and it would be 3.25 times 10 to the minus 3. In that case, minus 3. When we turn something into scientific notation or write a number in scientific notation, all of the numbers before the times 10 part are significant, which means we should never gain or lose significant figures as you go from scientific notation to decimal form and so forth. This number here had 4 significant figures. This number here has 4 significant figures. This number here has 3 significant figures. This number here has 3 significant figures. If we had our 12,000 example there, we would write 1.2 times 10 to the 1, 2, 3, 4 places. And that is because these are the only significant figures, which is 2, and this guy has 2. Some of the only ways you maybe can get yourself to the correct number of significant figures is actually to write a number in scientific notation, because frankly, you could control how many significant figures you need by putting more zeros or not zeros sort of in it. You know, if I needed 3 Sig Figs here, I could just write something like this, and now I have 3 Sig Figs and so forth. Do you need to write everything in scientific notation in this class? The answer is no. If you want, you can. You don't have to do it, but you should, obviously, since it's a chemistry class, right? Yes. You should try to put everything in the right number of Sig Figs. Do not give me 400 digits, yes, that run from the front of the page to the back. I've actually had that, like the person almost ran out of a room. They put so many digits down and they squeezed them all in at the end. All right, but more importantly about, instead of actually writing scientific notation, is what people truly lack is how to actually put that into your calculator. Yes. So that is something for sure in this class that you need to be able to do, or you will find yourself like, my number kind of looks right, but it's just like a little off, you know. It's like kind of right, you know, when they mess up and stuff. So on it, most people's calculators, there is actually a dedicated exponent button. On most people's calculators, it is either an EXP button, it is an EE button, or on some of the fancy new ones, which I'm sorry if you have one of these, no, I'm just kidding, is times 10 to the N button or 10 to the X button or something like that. These are actually your exponent buttons and what you should use when you enter a number in your calculator scientific notation. You should not use like the second button and the log button. You should not use the multiplication button or any of those buttons. So if you have something like 6.25 times 10 to the 13, you would hit on your calculator 6.25, you would hit your exponent button. On a lot of people's calculators, it'll go at 6.25, maybe put an E. It might go 6.25, pop up a couple of zeros. Maybe they put like times 10 underneath it or something like that. When you hit this button, that represents this part of the number, which means you don't need to hit the multiplication button. You don't need to hit like the caret button or any of those things. All that's left to hit is, and it will put a 13 there. It will turn this into a 13. And that is the proper way to do it. If you had a negative exponent, You would do it the same way. You would go 3.25, hit your exponent button. And again, I will do one of these two things. You then want to hit your negative button, which is a button that looks like this, or on some calculators, this. It is not the subtract button. Yeah, so it is one of those two buttons there. And then you would hit 3, and it will do your -3 and put those zeros as probably -3 as well. And that is the proper way to punch it in, and you should definitely do it that way. If you find yourself punching numbers in and you're like, I'm very close, but the exponent part of my answer is wrong, it is probably the way you were punching it in. Now, if you have this button on your calculator, which a lot of like the two-tone type calculators have it, and usually if you have that button, you also have the little circle dial button on your calculator. And the only difference really is in most cases, the way those calculators are programmed is you got to put parentheses around every single number. Otherwise, it will do the math incorrect. So if you were going to do, say, this number, you would actually have to start with the parentheses, type in 6.25, and then hit that button. And it will, on your calculator, show it to you as parentheses 6.25. It'll be a 10. And now you'll have like your little cursor blinking at you up on top. And at that point, you could then do the 13. And you will then have 6.25 times 10 to the 13. And now your cursor blinking at you next to the 13. Obviously, if you had a negative exponent, you would hit the negative button as well. That's really where this thing comes into play. Typically, you need to hit that right there on the right. That will bring your cursor down. And now you could actually close your parentheses like that, rather than like have a little parentheses up on top, or that might cause you an error. So that's the additional thing you have to do on a calculator like that. It's really, you got a parentheses around all the numbers. Otherwise, you're not going to get the right answer. The question on how to use calculators there in scientific notation. If you're not sure how to do it, just bring your calculator up to me. We'll figure it out on your particular calculator. Any questions on any of that there? Okay. We had that, right? By the way, before we move on from sort of measurements, right, there is a difference between accuracy, right, and precision. Right? Accuracy means how close you are to the true value, right? Precision means how close a set of numbers are to one another. So precision we use a lot of times to when we do multiple trials of an experiment, right? And we get the same answer every time, right? It's repeatable, talks about repeatability. Accuracy is how close we were to, you know, kind of what the true actual value is, right? So if we were playing darts and friendly gambling, which you should not gamble, but friendly gambling, and we threw our darts, I threw my 3 darts, and sadly, I missed the board on that one altogether. Am I accurate? Am I precise? I really shouldn't be playing darts, is what you're saying. I understand. It's okay. So in a friendly wager, I go, well, why don't we double or nothing, maybe? You know, I feel good right about now. I'm going to throw my darts again. And I throw my darts. Am I accurate? Am I precise? I'm precisely not accurate. Yes, that's right. I am precise, which indicates the idea that you can really do it wrong consistently, right? You could consistently do the wrong thing every single time and you get the same wrong answer. So, you know, I go, well, I'll just, you know, triple or nothing in this case, right? As I slowly edge towards the door. And I throw my dart. Am I accurate? Am I precise? I probably hustled you, yes? That's why you don't gamble. It's not good. You don't do that thing. So yeah, so we do want to be very accurate, obviously, when we take measurements and do experiments, and we want to be very precise. We want to be able to repeat the experiments multiple times and obviously come out hopefully with the same result. Any questions on that there? As we'll talk about in lab probably, right, we use something like % error, right, for accuracy. And that's where you take like your experimental value minus the true value divided by the true value and times it by 100. We use something like percent precision or something like that, or standard deviation, you know, to kind of talk about precision and repeatability. All right. Moving on for measurements, a couple other really big things, right? Hopefully that you learned was things like molar mass. Yes. What are the units of molar mass? Grams per mole, right? Grams per molar is the units of molar mass. We could get the molar mass from the periodic table by taking the number on the bottom there, right? Which is also known as the atomic mass, but in this circumstance, it is the molar mass. And that number means for carbon that there are 12.01 grams per every mole. Molar mass is grams per mole, which means you always do it per mole, and you always do it as based on the formula that's given to you, regardless of the coefficient that might be in the balanced equation. So if I had something like C6H6, to calculate the molar mass of this guy, this would be 6 times 12.01 grams per mole plus 6 times 1.008 grams per mole, which are the molar masses you would get from the periodic table. Or grab our handy dandy calculator here. Gets us something like 78.11 grams per mole is the molar mass. Typically speaking, it is 4 significant figures that we pull off the periodic table when we do molar mass. Depending on the periodic table, they may give you more or less sort of values, but 4 is typically what we do. We could use molar mass as a conversion factor, and we use it as a conversion factor to go from grams to moles, right? And moles to grams, right? That is our conversion factor to do that. If I had 42.5 moles of C6H6 and I want to know how many grams, we would figure that out by using the molar mass as a conversion factor. And of course, setting it up using what we like to call in the business dimensional analysis. Yes. 78.11 grams per mole, where we show the units canceling and everything set up as like this, which is how you should do it. We are basically multiplying across the top, right? Dividing by whatever's on the bottom. The moles of this guy here will cancel, leaving us with grams up on top. And if we do that, we end up with here. We end up with 3319.675 grams. How many sig figs should this one have? Should have 3. Most conversion factors are definitions, right, or what are referred to as exact numbers, which means they could have multiple amount of significant figures. And we usually don't look at exact numbers, right, when we are doing calculations, which means we default back to our original guy here. And since we're just multiplying and dividing, that should be 3 significant figures, which takes us to here, which means we should have 3320 grams, right? What we should end up with. Any questions on that there? Grams to moles, moles to grams. We do a lot in here. You need to be able to do those calculations. While we're here, we'll talk about our friend Avogadro's number there. Avogadro's number. And that means that 1 mole of anything, right, is 6.022 times 10 to the 23. These could be atoms, right? They could be molecules, they could be particles, they could be pizzas. And we really use Avogadro's number to go from moles to molecules or atoms, right? And back and forth. So we really do go from moles to either atoms or molecules or backwards, right? If there is no mention of atoms or molecules, then you should not be using Avogadro's number. But if there is some mention, you usually will use it to go to moles. Relationship would be obviously something like in 1 mole of hydrogen, right? There is 1.008 grams of hydrogen and 6.022 times 10 to the 23 atoms of hydrogen that would be there. Any question on Avogadro's number? You could also use it obviously as like a dimensional analysis sort of conversion factor. Okay, the next sort of thing is really important, which is equations, right? Just in general, right? On the right-hand side, there are reactants. On the left-hand side is our reactants. On the right-hand side is our products, right? Reactants is what we start with. Products is what we end with. On top of the arrow is a lot of times written things, maybe like platinum, maybe like H+. A lot of times on top of the arrow, we have what are referred to as catalysts, right? And catalysts are not reactants. They're not products. They are not used up in the actual reaction. They're there really just to facilitate the reaction occurring faster. They do that by lowering the activation energy and allowing the reaction to proceed a lot faster. Obviously, all equations should always be balanced. And we balance the equations by changing the coefficients, right? Is what we change. Never the subscripts or anything like that. So we end up with a balanced equation when we do that, you know, something like this. 2 there, perhaps, maybe like a 3 there. So these are the coefficients that we change. And those are the only things that we change in this case. And from a balanced equation, right, we could use stoichiometry, right, to figure out how much product we may make, how much reactants we started with. We do that by looking at these coefficients, and these guys are what are referred to as the mole-to-mole relationship. There are 3 moles of hydrogen for every 1 mole of nitrogen. There are 3 moles of hydrogen for every 2 moles of NH3 you get, and 1 mole of N2 for every 2 moles of NH3. So in a basic stoichiometry problem, you typically balance the equation always in all problems, pretty much. You take what they give you and convert them into moles. So if they have grams, you use molar mass, right, to convert it to moles. You do the mole-to-mole relationship, and then you can do moles to some other unit like grams on the back end. We use stoichiometry because maybe they tell us we produced 20 grams of NH3. How much H2 did we start with? To figure out how much of that we started with. There's also limiting reagents, yes, and limiting reagent problems involves you to solve and figure out which one is the limiting reagent, and there's multiple ways to do that depending on how you were taught. My guess most of you were taught to just do 2 separate stoichiometry calculations and figure out which one produced the least amount, and that would be your limiting reagent and your theoretical yield. Some of you might have been taught to take the 2 reactants and figure out how much of one reactant you need to use up the other reactant. And if you have enough, then that's the excess reagent. If you don't have enough, that's the limiting reagent. Probably none of you were taught to use an ice table, I'm assuming, right? No. I know I teach it because you guys come onto this class and that's all we do is ice tables in this class. So those are multiple ways that you could do that. Other things that we do with stoichiometry is percent yield, right? Percent yield is the actual yield that you get when you do an experiment, right? Divided by the theoretical yield, which is the stoichiometry calculation of how much you should produce. Which is your actual divided by your theoretical times 100%. You want a high or low percent yield? I guess it depends on your outlook on life, but you probably want a high percent yield. That means you kind of did the experiment grid. If you had a low percent yield, that means you probably dropped most of it on the floor, right? You want a high or low percent error? Low, yeah, that's the one you want low. Percent error, you want low. Percent yield, you want high. Do you want over 100% yield? Probably not, because that also means you probably screwed up somewhere along the way, by the way, just so you know. So if you were the person in Chem 50 said, I got 120% yield, and go, yeah, I did 20% more work than everybody else. You did about 40% wrong work more than everybody else in that particular case. All right, so we got a little stoichiometry, got equation, but more importantly as well in this class is you do need to be able to write equations from words. You need to understand, what you will make as part of the reactions, and it helps out with the calculation part and the understanding of what's going on. So let's just kind of review the big classes of types of reactions that hopefully you understand. We'll start with, really, if you were taught perhaps correctly, that there really is two big categories of reactions. One really big umbrella of reactions are double displacement reactions. The other big umbrella of reactions are redox reactions. These are really the two big umbrellas of types of reactions that occur. Under double displacement reactions, they generally have this sort of setup, AB plus CD. And the way you can recognize it is these two guys are both ionic compounds, right? Ionic compounds are positive cation, negative anion. So positive, negative thing. In a double displacement reaction, basically the two positive guys switch partners, and you end up with two new ionic compounds on the back end here, which is positive, negative, positive, negative. Now, that's the big classification, double displacement reactions. Underneath that classification, double displacement reactions, are our friends, the precipitation reaction, which is basically this reaction, except one of these guys makes a solid, right? So it makes a solid. So a solid is produced, which is sometimes referred to as a precipitate, a PPT. That is based on everybody's favorite solubility rules. Yes. Like group 1 is soluble in everything. Nitrates, acetates are soluble in everything. Chlorides, bromides, iodines are soluble in everything except for silver, lead, and mercury, right? So those type of things, perhaps you remember. So those are precipitation reactions. The other sort of subcategory of double displacement reactions are acid-base reactions, which we come across a lot in here. Acid-base reactions. They're sometimes called acid-base neutralization reactions. And when you take an acid and a base, especially a strong acid and a strong base, you basically make two things. You make a salt and water, right? And a salt is really just an ionic compound, and water obviously is water, which is a liquid, right? By the way, these are some symbols that we commonly see in equations: solid, liquid, gas, and AQ is aqueous, right? Is there a difference between L and AQ? The answer is yes. Otherwise, we would probably just use one symbol, I'm assuming there, right? The difference is L is a pure liquid. Like if you had water by itself, right? That would be a pure liquid. If you take a water by itself and you add some sodium chloride, that's a solid, right? The sodium chloride will dissolve in that, and that will give you a sodium chloride solution, which is aqueous. So something that is aqueous is really a solution, usually made by dissolving something in a larger part there. Now, looking at, say, a acid-base reaction, like our friend here, a little hydrochloric acid, right? Plus some sodium hydroxide. Again, this is really a positive, negative, going to switch partners this away. That will give us some H2O and some sodium chloride here. And that is our salt and water in this case. Again, the salt just is backwards there. So let's try that again. Sorry. the water the wrong way. All right, so this is still water. There we go. That is a salt there. This right here is what we like to call in the business there a balanced molecular equation, right? We could also represent what's going on here by another equation by breaking apart everything that is a strong electrolyte and break it apart into this situation here, which both hydrochloric acid and sodium hydroxide are strong electrolytes. Electrolytes are things that when they go for a swim break apart into ions and conduct electricity. Yes. Light bulb goes on, light bulb goes off, right? This type of reaction here, equation here, actually is what is known as the total ionic equation, or sometimes referred to as the complete ionic equation. In this equation, we break apart everything that's really a strong electrolyte. We keep together anything that's a liquid, anything that's a solid, anything that's a gas, anything that is a weak electrolyte, which will mainly stay together and not break apart. When we do this type of equation, this is where we can find our other favorite things, which are, we look on the left-hand side and the right-hand side of the equation, we will be able to find ions that look the same, and these are what are referred to as spectator ions, right? We cancel out the spectator ions, and what we are left with is an equation which is known as the net ionic equation, which basically tells us what is really going on in this reaction. So what is really going on in this reaction is the H plus from the acid, the OH minus from the base are coming together basically to form water. That's really important because there's really three reasons why a reaction takes place. What are the three reasons why a reaction takes place? You form water, you form a precipitate or a solid, and the last reason why a reaction takes place are those reactions right there. You have electrons being transferred. Those are the three driving forces, is sometimes called, as to why reactions take place, is electrons being transferred, solids being formed, and water being formed. That's really the basis of all reactions, is those three things. Now, those are the two types of double displacement reactions. So let's talk a little bit about redox reactions, and we will get more into it a little bit later on because we do a whole chapter on redox chemistry, basically. But there's really two things in redox reactions, just in general, what is referred to as an oxidation occurring, and that is the loss of electrons. That's one definition. Reduction means that something has gained electrons. People sometimes remember this as Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Other people are fond of the oil rig. Oxidizing is losing, reducing is gaining. The idea here is things are transferring electrons, and it goes from one place to the next. If somebody loses electrons, do they become more positive or more negative? They do become more positive because they have more protons than electrons, right? So they become more positive. And if somebody gains electrons, they become more negative because they now have more electrons than they do protons. Simple way to figure out who's doing what is actually just a simple number line. If you look at what is referred to as the oxidation state, or like the charge, if you will, and if that guy gets more positive as it goes from reactants to products, it's going through oxidation. And if it gets more negative, it is going through reduction. So there are some examples of these type of reactions. So once again, the redox reaction is the big classification. It involves really electrons being transferred. Underneath that umbrella, you have your synthesis or combination reactions. And that is typically when two things make one thing, right? So like magnesium plus some oxygen makes a little magnesium oxide. Talked about this morning. evacuating people when they do this experiment. Two things make one thing is a synthesis or combination reaction. If we actually look at what's happening in terms of, say, the magnesium has no charge here when it's by itself. Over here, it actually becomes +2. The oxygen is in its natural state, has an oxidation state of 0. And over here, this guy is actually a -2 charge. That's an ionic compound on the right, +2, -2 comes together. If we look at the magnesium, it starts at 0, ends at +2. It is being oxidized, right? It is becoming more positive. The oxygen starts at 0 and ends at -2, is becoming more negative and is going through reduction. That is always what happens when a metal and non-metal get together, correct? Metals are typically the ones that lose electrons. Non-metals are the ones that gain electrons, which is why they are negatively charged and those guys are positively charged. So a synthesis combination reaction is a subclassification of a redox reaction. In addition, we also have the opposite reaction, which is a decomposition there. And that is basically when one thing breaks apart into two things. A single replacement reaction, it falls under these as well. And that is when you have one thing plus another. And this is typically an ionic compound. This is something that has no charge by itself. If this was, for example, a metal, it would come in and kick out the positive guy, make a new ionic compound, and this guy would come out by itself. So, for example, if you did something like zinc metal plus some hydrochloric acid, the zinc does not have any type of charge at this point or oxidation state. It is by itself. When it comes in, it will become positively charged. So it's going to kick out the positive hydrogen there. When you kick out hydrogen, in this case, you make hydrogen gas, plop, plop, fizz, fizz, bubbles, you see at that point. Not so much plop, plop, fizz, fizz, probably. And you make a little zinc chloride action happening. And probably a little balancing would be the right thing to do in this situation as well. That is a single replacement reaction. That is also a redox reaction because the zinc is going from 0 on the left to +2 on the right, it's becoming oxidized. The chlorine on the left is actually -1. The chlorine on the right is -1. There's nothing happening to the chlorine. It's actually the hydrogen that is going from +1 on the left to 0 on the right. And again, if you're not sure, +1 on the left, 0 is going to the left. It is becoming reduced. So it's actually the hydrogen becoming reduced in this case. Those things always occur together. Somebody gets oxidized, somebody else gets reduced. It happens together. And a single replacement reaction is really a redox reaction that's occurring. The last one that sort of falls under this category is a combustion reaction. And most people, when they think of a combustion reaction, think about the organic combustion where you have an organic guy, which is something that has carbon, hydrogens, and oxygens plus O2, makes CO2 and water, and you get heat, like when you light a Bunsen burner like this guy right here, right? It's the methane coming out, the oxygen there, a little spark, you get fire, propane, butane. But technically, the basic definition of combustion is simply you just need some O2 right about there in an equation, and it technically is a combustion reaction, which actually means the magnesium and the oxygen there is technically a combustion reaction, actually, believe it or not. Most people would probably call it a synthesis reaction or a redox reaction, but it's actually a combustion reaction as well. And it just actually has to be the O2 present on that side. So synthesis, combination, decomposition, single replacement, combustion, those are all examples of redox reactions, and they all can be classified in that way. For us, we will see a lot of redox reactions in that chapter that involves obviously redox, but for us as well up front, we will see a lot of acid-base reactions, and you need to be able to write the products of those reactions. Otherwise, it's going to make a very difficult day for you as you go through those chapters. So understanding how to write these reactions is really, really important for your success here. And you will not always be given the equation. You will most likely in this class be given everything in words and just the reactants, and you've got to be able to figure out and write correctly you know, what you get on the product side, and obviously balance it correctly and stuff like that. Any questions on different types of reactions or anything like that, or equations? Okay. Other important things for sure is our good friend solutions, right? A solution is actually two parts, right? In a solution, you have what is referred to as the solute, which is the smaller part of the solution, and the solvent, which is the larger part of the solution. Both of those guys together make up a solution. Like my example a second ago, where we had pure water, which is a liquid, plus some sodium chloride, which is a solid. You mix them together and you get a sodium chloride solution, which gets the aqueous symbol. And that is typically what solutions give you, is the aqueous symbol. And when we talk about solutions, there are certain concentrations that we come across a lot. We won't go over all of them, but the one that's really important is molarity, big M. Yes, that is molarity. Molarity is technically moles of solute per liter of solution. Not to be confused with little m. Little m is what in terms of concentration? Do they teach you little m? Molality? Yes, anyone? Yeah. Colligative properties, boiler point elevation, freezing point depression. They teach that anymore? No, they don't teach that anymore. All right, well, you know, we'll send everybody back to Chem 50 for that later. All right, so this is basically moles per liter is molarity. I'm pretty sure they don't teach you normality either, I'm assuming as well. You think of this like a formula, right? You can rearrange it where liters there would be moles divided by molarity. And then obviously one we use a lot is moles would be liters times molarity. When you use a molarity by itself, you do need to make sure the volume's in liters, so everything properly cancels out. If you have something like 4.50 big M sodium chloride, which is 4.5 molar is how it's worded, you should really, when you're doing calculations, get rid of the big M and go with 4.5 moles of sodium chloride per liter. And you can use that as a conversion factor. A liter is 4.50 moles. And I would recommend doing your calculations like dimensional analysis. Most of the time, in my experience, people that leave the big M, frankly, have no idea where the liters is, or if it's even there, right? Or anything like that. Am I dividing it? Am I multiplying it? Most people don't really know. So, you know, if I had 25 milliliters of a 4.5 molar sodium chloride solution, how many moles would that be? I could use my 25 milliliters. I could turn this into my conversion factor. And I obviously would need to do a conversion here. So, right, there is how many milliliters in a liter? There is 1,000 milliliters in a liter, right? That's going to move my decimal place which way? This way, yes. 3 places to the left, right? And now we have it in the correct unit, and we can set it up using really the molarity like this. Liters will cancel, and we will end up with, in this particular case, 0.1125 moles of sodium chloride. Is that the right number of significant figures, by the way? How many sig figs should I have? Should have 2, right? This is 3, and that is 2. So we really should go right about there, right? Now that I have the moles of sodium chloride, how would I figure out how many grams that is? I would use the molar mass of sodium chloride from the periodic table. And if you do that, that's 58.44 grams per mole. We would go 58.44 grams per mole of sodium chloride. The moles would cancel. We would multiply that by the 0.11, and we would end up with like 6.6 grams of sodium chloride would be needed, right? So these are really important calculations, taking volume and molarity and multiplying them together to get to grams and things of that nature. If I multiply milliliters times molarity, do I get moles? I don't. I get what are known as millimoles, right? Which is okay if you then divide it by milliliters, because it will actually go back to molarity. But you should, if you're using molarity by itself, convert the volume into liters. Also, when we talk about solutions, it is the dilution, right? Dilution is where we take more solvent and add it, and the moles of the solute before the dilution equals the moles of the solute after the dilution. There is a nice equation with most people use, which is M1V1 equals M2V2 before the dilution, after. That is molarity and volume, molarity and volume. M1 and V1 is usually the more concentrated solution. M2 and V2 is the least concentrated or less concentrated solution. Some people are taught C1 V1 equals C2 V2, same deal. C is just generic for concentration, because technically you could use anything like percent composition, mass percent, mass volume percent, things like that. But most of the time we use molarity, so most of the time we're using this. Now, in this equation, you can use milliliters as long as you use milliliters on the other side, and it all works out okay, or you can convert it to liters. Is this the equation we use for like titrations and doing stoichiometry? And the answer is no. That's the wrong equation to use. You get lucky occasionally, but you don't get lucky all the time. So sometimes people are taught to use that for titrations and stoichiometry. It works in a very specific aspect of a one-to-one relationship. If your stoichiometry is not one-to-one, you will get the wrong answer if you try to use that. So keep that in mind. Now, we use dilutions obviously to make solutions, but we also see it occur in different places. So for example, to finish up here, let's say we were going to make a solution, and in the little lab manual it says solution number 1, you're going to use 0.25 molar, we'll go with sodium chloride. And in solution 1, you're going to use 0.025 molar. We'll do a little HCl. I'm not sure why we're mixing all these things. And then we'll add a little deionized water to the mix. Why not? So let's just say we used 2 milliliters of this guy. Let's say we use like 6 milliliters of this guy here. And we'll use like 2 milliliters of this guy. Actually, I'm going to give a couple extra Sig Figs there. And 2 milliliters. All right, so I go to make my solution in my generic tube, and I drop in there my 2 milliliters in my bad quality controlled tube that's sort of straightish. My sodium chloride, I drop in there my 6 milliliters of my HCl, and I drop in there obviously my 2 milliliters, not drawn to scale here, of my water in there. And I want to know, what is the molarity of the sodium chloride in solution number 2? I guess I changed the number in number 2. Is the molarity of sodium chloride in solution number 2 0.25 molar? It is not, right? Because it was right about at this point, but as soon as I add my 6 milliliters of the HCl, my 2 milliliters of water, and they all start to do the mixy, shaky, maybe not so much shaky, but a little bit of mixy here. They have all now mixed together, correct? Which means as you add volume, the molarity stays the same, or does it change? It actually changes. What stays the same is actually the moles of the solute, right? Because that's throwing so much in there. So this is actually a dilution situation that's happening here. We have the molarity of the original sodium chloride. We have the volume of it that we use. The total volume of our new mixture is 6, 2, and 2, which is 10 milliliters would be our total volume. To figure out the molarity of the sodium chloride in our mixture, we could use the dilution equation to do so. M1 would be the more concentrated sodium chloride. V1 would be how much of it we used. M2 would be what we're looking for in terms of its concentration in the mixture. And V2 would be our total volume, which is all three of those guys together, which would be 10 milliliters. Give it a go. We end up with 0.25 times 2 divided by 10. And once again, here, I do not need to actually convert it into liters here because we got milliliters on both sides. It all works out. And we end up with something like our concentration of the sodium chloride in that solution, if I looked at it right there, is 0.05 molar sodium chloride. So that is something we do a lot, especially we do a lot of it in lab. We mix together everything, and you need to figure out the concentration of that guy in the actual mixture together in the solution. And a lot of times what you're doing, which you might not even realize, is actually you're doing dilutions of these things. M1 V1 equals M2 V2 is something we use a lot in the lab to figure out concentrations of stuff. Any questions on that? We obviously could do it for the HCl as well. It would be the same kind of calculation, except for the HCl, it would be 0.025 times 6 divided by 10. And that would give you the concentration of the HCl in that mixture as well. So if you pour a solution from the main bottle that has a molarity into another bottle and don't do anything to it, the molarity is the same. But as soon as you add other solutions in with it, you are actually doing dilutions at that point, and the molarities change and the concentration changes. So you have to account for that in your calculations. Any questions on that there? All right, well, that was the highlights of Chem 50. I think that's most of the stuff. Again, there's that module in the Canvas site that has some more of the review stuff. But really, for this class, you got to know molarity. You got to know dilutions, got to know how to calculate molarity. You have to know how to write equations and balance equations. And you have to know about molar mass and converting things. You need to know how to really do those things if you want to do well in here. Any questions on any of that stuff?